And just like we've done before, we can construct the vector equation of a plane. However, this time things are going to be just a little bit different. Not so much in quality, but in quantity. In the following sense. So we're going to, just like before, we're going to consider a plane, and we're going to consider a point on this plane, and we're going to think of two direction vectors on it. And this is where the difference comes in. For a line, of course, the line only has one direction, so we only needed to identify one direction vector. In this case, for a plane, we need two direction vectors. They don't have to be perpendicular, but they cannot be parallel either. Otherwise, of course, we get squished down to just a line. Okay, but let's say that we have a point and two directions which are on this plane. Now, what we can do is we can pick any other point on the plane, and notice that the vector x, just like, well, first of all, algebraically it's quite obvious. X is going to be equal to p plus x minus p. Well, you do the algebra, you realize that it's right. But what does that mean geometrically? Remember, once again, I'm identifying points with vectors. So I'm saying the vector that goes from the origin to the point x can be obtained as the vector that goes from the origin to the point p, and then add the vector that goes from p to x. That's x minus p. Okay. But I can write any such vector from p to x as a linear combination of the two direction vectors. How do I do that? Well, all I had to do is start from p, go for a while along the direction of d1, and I'll have to use an appropriate multiple of d1 to get far enough where I want to go, and then add a multiple of the second direction vector. This can always be done, and therefore my generic point on the plane can be written in this way as an initial point P plus some multiple of the first direction vector plus another multiple of the other direction vector. So notice this is the same as the vector equation of a line, only instead of having just one direction vector, we now have two direction vectors. So this is the vector equation of the plane, and just like before, if we separate the components, we can write those equations in this way. Of course, now because we have several equations and two direction vectors and so on, the notation starts to be a little bit heavier. But this, just like before, is called the parametric equations of the plane. Now, what can we do with all this? Well, we can use all what we know about vectors and planes and dot products or perpendicularity and all these kind of things, and as well as linear systems, to ask some questions about lines and planes, about how to construct them or how to analyze their properties. For instance, again, keep in mind that a line in 2 dimensions can be written down as the general equation. A plane in 3 dimensions can also be written down in terms of its general equation. Well, what about a line in 3 dimensions? Right? So how can I get a line in 3 dimensions? How can I identify that? Well, the one thing I can do is I can think of the fact that a line in 3 dimensions can be thought of as the intersection of 2 planes. Think of the blue plane and the green plane, and they're not parallel. So where do they intersect? They intersect in a line. Okay. Therefore, the line consists of all the points which satisfy the equations of both planes. But that's exactly what we mean by a system. And so a line in 3D is given by a system of 2 equations in x, y, and z, where a1, b1, c1 is going to be the vector normal to the first plane. a2, b2, c2 is going to be the vector perpendicular to the second plane. Okay? And so we can use this kind of information to analyze the connections between these lines and planes and so on. Now, also, what is the vector equation of a line in 3 dimensions? Well, think about it. What do we need in order to get the vector equation of a line in 3D? We need a point. We need to find out where this line is planted, and also we need to find a direction. But of course, the direction is given by a vector. But once we have these two, the rest is exactly the same as it was in 2 dimensions. The equation of the line, or the generic point on the line x, is going to be given by this initial given point P plus some multiple of the direction vector. Notice this is exactly the same as the one in 2 dimensions. So what's changing? What's changing now is that x, p, and d are three-dimensional vectors, not two-dimensional vectors. Otherwise, the equation is exactly the same. So we have the same information, so therefore same kind of equation, and again, we're in class, we're going to be looking at a whole bunch of questions that we can ask about lines and planes and their intersection and their relationship and so on and so on. That all can be answered by simply thinking about one of these linear algebra style equations, either of lines or planes.